Thank you for joining us for another HPL seminar, our last one for the semester, and then we're gonna take a little break and come back in the fall. So thank you for joining us. And today, for the last seminar of the semester, it is my pleasure to introduce our speaker, Sierra Sweeney, who is a master's student in biomedical engineering under the co-supervision of Dr. Amin Kumaili and Dr. Jalal Abu Darda. She completed her Bachelor of Science in Human Performance with a minor in biology at the Northern State University in South Dakota in 2024. During her undergraduate studies, she investigated lower limb force production in high school and collegiate triple jump athletes. Outside of her research, Sierra mentioned that she has co-founded the track and field club Grit Athletics in Nova Scotia alongside her dad. And today she will be presenting her work on cycling kinetics on an ergometer designed to quantify asymmetry during experimentally induced pain. Thank you, Sierra.
Thank you. So thank you guys for coming today, and welcome to my presentation. We're going to look at cycling kinetics on an ergometer designed to quantify asymmetry under painful conditions. So as a competitive track and field athlete, I've always been fascinated by human movement and performance. Throughout my athletic career, I've also experienced several injuries and have seen firsthand that recovery is not the same for everyone. Some people recover faster, some face ongoing challenges, and pain itself can dramatically differ between individuals. My interest in these topics grew during my undergraduate degree at Northern State University in South Dakota. Here, I combined my passion for triple jump and research, examining how the large forces experienced by the lower limbs during the event may contribute to injury risk. That project deepened my appreciation for the complex relationship that exists between biomechanics, performance, injury, rehabilitation, and pain. Those experiences ultimately sparked my interest in developing tools that can better capture individual differences in movement and recovery. The ergometer that is used in this research was designed with that concept in mind, to provide detailed, objective measurements of movement and asymmetry that can help support more personalized rehabilitation strategies. So just an outline of what we're going to go over today. We're going to talk a little bit about the background and the rationale for this project. We're going to look at study 1, which explored the reproducibility of the sensors in the ergometer. Study 2, which explored inter-individual differences in response to pain. And then we're going to talk about implications, conclusions, and future directions for this research. So lower limb asymmetry refers to differences in force, power, or strength production between the right and the left limbs. While small asymmetries are normal, larger asymmetries can negatively affect movement and function. These asymmetries are commonly observed in clinical populations, such as those with knee osteoarthritis, ACL injury, stroke, and joint replacements. Although the underlying conditions differ, they often produce the same outcome. One limb contributes less to movement than the other, causing the individual to compensate by relying more on the opposite limb. Over time, this redistribution of force can increase injury risk and pain, reduce physical function, and limit physical activity and rehabilitation success. Because of these consequences, accurately identifying and monitoring asymmetry is important for developing effective rehabilitation strategies. The Normalized Symmetry Index, or NSI, can be used to quantify the percent difference between the output of one leg versus the other. It can be calculated with this formula. In healthy individuals, this value is generally close to 0, with asymmetry levels below 10% being considered normal. Anything above 10% can become problematic. These two graphs here represent power, which can be defined as force output times angular velocity. The graph on top represents the graph of a healthy individual, and as you can see, the right and left limbs are relatively the same. Down below on the bottom graph, you can see that the right leg, which is the blue line, is demonstrating much less power than the left leg, which is showing asymmetry. Now, cycling is widely used in rehabilitation because it provides a low-impact environment that reduces stress on the lower limb joints while allowing patients to exercise at meaningful exercise intensities. Unlike many weight-bearing activities, cycling maintains continuous contact between the foot and the pedal, allowing for better force transfer between the ankle, knee, and the hip. This can reduce pain during movement and allow individuals to tolerate greater training volumes. However, cycling is not without limitations. Even though it reduces pain and improves exercise tolerance, individuals with existing asymmetries may continue to offload the affected limb and rely more heavily on the unaffected side. As a result, abnormal movement patterns can still occur. Therefore, the effectiveness of cycling-based rehabilitation may depend on our ability to monitor how much each limb contributes during exercise. This highlights the need for devices capable of quantifying bilateral force production and detecting asymmetry in real time. Let's look at some of the current ergometers that are used. The Load Excalibur Sport device is an ergometer which is currently used in sport and athlete settings to test and measure pedal force performance throughout various tests. It's equipped with pedal force sensors and strain gauges that allow for analysis of left and right pedals separately. But a downfall is that it lacks handlebar and seat post sensors. Without the ability to assess those parameters, clinicians cannot determine whether patients are offloading to other areas of the body. The SRM Ergometer is equipped with strain gauges, which measure rider torque and power on the pedals, which can be displayed in real time. The forces that are recorded on the pedals are only measured in 2 dimensions. It's also not equipped with seat post or handlebar force sensors. Finally, the Motomet therapy device was specifically developed for those with movement restrictions and incorporates motor-assisted cycling to facilitate torque generation. Although this may be useful in patients with reduced function, it is not a feasible device for those who can exert larger amounts of force on their own. As a result, rehabilitation progress and higher functioning individuals may be limited. Several researchers have attempted to quantify lower limb asymmetry during cycling, but important limitations remain. For one, they are all primarily pedal-based measurements. Many also only looked at the left versus right limb contribution rather than quantifying asymmetry. Additionally, many studies use the same absolute workload for all participants, which may have resulted in different levels of fatigue and metabolic stress. Finally, very few studies have looked at how asymmetry evolves during a fatiguing cycling task. As a result, there is still limited understanding of how force redistribution occurs during rehabilitation exercise, highlighting the need for a comprehensive multi-sensor assessment system. To address limitations in previous research, our lab recently developed a new instrumented cycle ergometer. It is built from an Echelon EX5 stationary bike and integrates multiple sensors to capture whole body cycling biomechanics in real time. As shown in the figure, the system consists of several key components. A crank encoder is mounted to the crank system and continuously tracks crank position throughout the pedal cycle. This allows all biomechanical measurements to be synchronized to a specific crank angle, enabling phase-specific analysis. The system also includes instrumented force pedals that measure 3-dimensional forces and moments applied to each. This data is also used to calculate pedal torque, power output, and lower limb asymmetry throughout the cycle. To capture whole body force distribution, the device incorporates a 6-axis force sensor beneath the saddle and force sensors within the handlebars, along with grip force sensors. These measurements allow us to determine whether individuals redistribute forces to other contact points. Together, these sensors provide a comprehensive assessment of cycling biomechanics and that cannot be captured using pedal measurements alone. This image here illustrates the pedal and crank coordinate system that is used for data analysis. The figure shows the 3 orthogonal pedal force components measured by the force pedals, as well as the definition of the crank angle that is used throughout the study, with 0 corresponding to top dead center and 180 degrees corresponding to dead center on the bottom. I would also like to mention that a new aspect of this device is the assisted motor that is placed on the front. However, this study only focuses on the reproducibility of the sensors and therefore is out of the scope of this research. The objective of the first study was to evaluate the reproducibility of the sensors on the ergometer, and it was hypothesized that it would provide reproducible measurements even under fatiguing tasks. In this study, 18 healthy individuals participated. After screening and informed consent, they completed a total of five lab visits. The first session is a familiarization visit, where participants were introduced to the protocol and the device. During sessions 2 and 3, participants completed an incremental cycling task, where they completed a 3-minute warm-up at 40 watts and 70 RPM, followed by a 20-watt increase every minute until task failure. In sessions 4 and 5, participants completed 2 trials of 70% of their peak power output that was determined from the incremental task, once again until task failure. Data was collected at 250 Hertz, but it was averaged every 5 degrees over the entire frame for analyses as is represented here. To quantify asymmetry between limbs, I calculated the NSI using the formula that was presented earlier for both force and power. Because here we were only interested in the magnitude of asymmetry rather than which leg was producing more, we looked at the absolute value. Data was averaged for 5 time points throughout the test, and changes across time and between sessions were assessed using repeated measures ANOVA. Reliability between sessions was assessed using interlast correlation coefficients. First, if we look at results for pedal force and power, we'll look first at pedal force in panel A. The dashed lines represent the incremental cycling test, where pedal force increased progressively as participants approached task failure. This is expected because greater force production was required to meet increasing workload demands. In contrast, the solid lines represent the constant load test where workload remained fixed. The pedal force remained relatively stable throughout the protocol. There were no significant session effects or interactions in either protocol, indicating excellent reproducibility. Next, if we look at right pedal power, we observed a very similar pattern during the incremental test. During the constant load test, power also showed a small but significant increase over time, despite the workload remaining fixed. This likely reflected subtle changes in cycling mechanics as the task progressed. However, there were still no differences between sessions. Now we're going to look at handlebar force and seat post results. So in panel C, we can see right handlebar force. During the incremental test, which is once again represented by the dashed lines, there was a small but significant change over time, suggesting that participants slightly altered how they interacted with the handlebars as exercise intensity increased. In contrast, during the constant load protocol, handlebar force remained relatively stable throughout the test. Once again, there were no session effects or interactions, indicating that they were highly consistent between testing sessions. Now, if we look at panel D, we can see seat post medial-lateral sway. Unlike pedal force and power, seat post sway remained relatively consistent throughout the incremental protocol. During the constant load test, a small but significant time effect was observed, which is indicated by the $sign, suggesting a modest change in sway as the task progressed. However, again, no significant session effects or interactions. Finally, we examine the reliability of NSI for force and for power. First, let's look at NSI force, which is in panel A. Asymmetry values remain relatively stable throughout both the incremental and constant load protocols. There were no significant effects of time, session, or interactions, indicating that force asymmetry was highly reproducible between the testing days. If we look at panel B, NSI for power also remained generally stable across exercise. A small session effect was observed during the incremental test, which is indicated by the $sign, suggesting a slight difference in overall asymmetry. However, again, no time effects or interaction effects, indicating the pattern of asymmetry remained consistent throughout the protocol and trials. So overall, if we talk about study 1, the device produced reproducible results even under fatiguing conditions and sessions, and it was reproducible in quantifying lower limb NSI. Supporting this, ICC values for all primary outcomes range from 0.7 to 0.99, which indicated good to excellent reliability across both sessions and trials. Now, as we move into session 2, let's talk about pain. So it's known that pain is an unpleasant sensory and emotional experience associated with actual or potential tissue damage. It is common in clinical populations, such as individuals with neo-ed, and it can significantly impact physical function and exercise participation. In rehabilitation settings, pain may lead to premature termination of exercise, which reduces overall cardiovascular and overall rehabilitation benefits. It can also alter movement behavior by promoting protective unloading of the affected limb. Despite its relevance, there is still limited research examining how pain specifically influences cycling biomechanics and interlimb asymmetry during exercise. Several experimental pain models have been used to investigate how pain influences motor control, including blood flow restriction, which creates muscle pain, and hypertonic saline injections, which create joint pain. These models have shown that pain can reduce force production and alter neuromuscular control during exercise. However, they have important limitations, including poor ecological validity and an inability to reproduce steady-state joint-specific pain that is experienced in clinical populations. More recently, researchers have developed electrical stimulation models that can induce stable, task-relevant knee pain. For example, Galina and colleagues demonstrated that electrical stimulation could be linked to limb loading, causing participants to unload the painful limb, specifically during walking. More specifically, knee flexion decreased during the push-off phase, which is demonstrated by this graph above. Building on this work, Cabral and Alt showed that movement-evoked knee pain produced greater reductions in force than tonic pain, highlighting its ability to generate meaningful motor adaptations. These findings suggest that electrically induced movement-evoked pain produces a more clinically relevant model for studying pain-related changes in motor control. Therefore, if we look at study 2, the objective was to assess torque, power, asymmetry, and inter-individual biomechanical responses during cycling when exposed to pain, and it was hypothesized that movement-evoked knee pain would alter cycling biomechanics and loading patterns, with responses varying between individuals. To induce movement-evoked knee pain during cycling, we developed a custom closed-loop stimulation system. As participants pedaled, the ergometer continuously measured pedal torque in real time. The amount of electrical stimulation delivered to the knee was then automatically adjusted based on how hard the participant was pushing. So here, we can see there's a lower amount of torque and not as much stimulation. Whereas over here, there's slightly higher torque, so now there's a little bit more electrical current. We should note that this closed loop process was repeated 100 times per second, and that stimulation was only applied during the downstroke or the push phase of each cycle. It was either delivered to the left or right knee to account for potential effects of limb dominance between participants. This video here shows the setup and system. Just note that the white tape is EMGs that we did record, but there was some issues with noise during analysis, so results from the EMGs are not reported here. You can also see that the electrical pads are placed on the left knee for this participant. So though each one of those green kind of spikes is a cycle, and it demonstrates how much electrical current was being supplied during that cycle. So for this study, 23 healthy participants participated. They completed 2 lab sessions that were separated by 48 hours. In the first session, they were familiarized with the cycle ergometer and the setup. They then performed an incremental cycling test to determine their peak power output. This test was very similar to what was done in study 1. The second session involved the main experimental trials under pain and no pain conditions. The participants completed 8 randomized 2-minute cycling trials at 60 RPM, which were all constant load trials, and 4 conditions. Condition 1 was a low low intensity experimental condition where pain was calibrated to about a 2 out of 10 pain level. The second trial was a low intensity control, which was at the same power output as the experimental condition, just with no pain this time. We then had a high intensity experimental condition, and this was calibrated to about a 6 out of 10 pain. And then we had a high intensity control condition, which was the same power output as the experimental condition, just with no pain this time. So torque and power were calculated for every pedal cycle. And again, because electrical stimulation was only applied during the downstroke phase, analyses only focused on that phase, which was 0 to 180 degrees of the pedal stroke. To assess the interlimb loading, we calculated NSI, which was the formula we used from earlier, where positive values indicated greater reliance on the pain leg and negative values indicated greater reliance on the non-pain leg. Variability of movement was also quantified by calculating the coefficient of variation. So first, let's look at some results from torque. Here we can see the control test without any stimulation, which is represented by the blue. As we can expect from a healthy participant with no pain, the torque of the left and right legs were relatively the same. We can see an equal contribution from both limbs. Now, the red is the experimental condition, where one leg received pain. Results show that due to pain, torque decreased in the painful limb, and the system was able to create asymmetry. We can see that this reduction was compensated for by the other limb. At lower intensities, the results were not as significant or as apparent as the higher intensity. This means that some individuals were able to tolerate the pain without affecting the cuddling mechanics. Now let's look at NSI. This graph shows push phase asymmetry for torque, or how torque was distributed between the two legs. Red represents the experimental condition and blue represents the control condition. In the graph, in the high intensity condition, which is graph C, participants shifted torque production away from the pain leg and relied more on the non-pain leg during the pain condition, which resulted in greater asymmetry. A similar pattern was observed in the low intensity condition, where participants also redistributed torque away from the painful limb. However, as shown by the individual data points and the connecting lines, responses varied between individuals. Overall, these findings suggest that pain altered torque production, primarily changing how work was distributed between the legs, rather than producing a uniform reduction across all individuals. But now let's talk a little bit about individual variability. An analogy that Dr. Jalal used when we were first trying to figure out our results is learning how to ice skate. When people first step onto the ice, they often adopt one of two strategies. Some become very stiff and restrict their movements because they're afraid of falling or hurting themselves. Others do exactly the opposite, making large, uncontrolled movements and waving their arms to maintain balance. These two responses represent different levels of movement variability and responses to new environments. The first skater demonstrates very little variability, while the second demonstrates excessive variability. So, to quantify the individual differences, we examine how variables change between the experimental pain condition and the control condition using a percent change formula. This helped to compare the change between the experimental and the control condition. This was done for both torque, power, and their corresponding NSI, as well as the coefficient of variation of each variable on the pain leg and the non-pain leg. The difference in NSI between conditions was calculated for classification, where negative values represented a redistribution of work towards the non-pain leg, while positive values indicated greater reliance on the pain leg. To characterize that inter-individual variability, participants were then classified using distribution-based categories derived from the group mean plus or minus 1 standard deviation for percent change towards in torque, power, NSI, and CV. For torque and power, only pain leg changes were used for categorization. When looking on the right, where values between the mean and 0 were categorized as small redistribution towards the non-pain leg, values between the mean minus 1 standard deviation and the mean were moderate redistribution towards the non-pain leg. Values that were below the mean minus 1 standard deviation were categorized as large redistribution towards the non-pain leg. And any values that were above 0 or positive were categorized as shifts to the pain leg. Now, when we look at the bar on the right, where we can see a stacked bar graph for power and torque, the two bars on the left represent power and torque respectively at high intensities, while the two on the right are low intensity. If we look at the second bar, so this one right here, we can see for torque at high intensity, there were about 5 participants with large redistribution towards the non-pain leg, 4 participants with moderate redistribution, 11 with small redistribution, and 3 with a shift to the pain leg. And that would apply to all bars. Overall, at higher intensities, you can see that most participants had small redistribution to the non-pain leg, whereas at lower intensities, there was not as large a shift towards the non-pain leg, and more participants actually shifted to the pain. This is the same distribution curve, but now we're looking at NSI. Much of the same pattern emerges here as power and torque. There are more individuals who shift to the non-pain leg at higher intensities as compared to the lower intensities. For change in CV, negative values were represented reductions in variability, so people who wanted to freeze during the experimental conditions, whereas positive values represented increases in variability or people who were potentially flailing everywhere if you want to relate it back to skating. So values that were between 0 and the mean were categorized as minimal changes in variability. Values between 0 and the mean minus 1 standard deviation were moderate reductions in variability. Values that were below the mean minus 1 standard deviation were categorized as people with large reductions in variability. Values between the mean and the mean plus 1 standard deviation as moderate increases in variability. And those that were above the mean plus 1 standard deviation were large increases in variability. When we looked at the stacked bar graph, we can see much more variability in responses as compared to the bar graphs for power, torque, and NSI. At higher intensities, there were more individuals who moderately reduced their variability, whereas at lower intensities, there were more individuals who had minimal changes. This demonstrates that when exposed to pain, each individual attempted to adapt in different ways, very similar to how individuals respond when they first step on the ice. Overall, under the experimental pain condition, participants reduced power and torque production in the pain leg, while increasing reliance on the non-pain leg. This indicated that pain altered cycling biomechanics by redistributing mechanical output away from the painful limb. However, a key finding was a large amount of inter-individual variability. Rather than responding uniformly, participants exhibited a continuum of responses, ranging from substantial compensation shifts towards the non-pain leg to very little change at all. These results suggest that pain-related motor adaptations are highly individualized. Therefore, relying solely on group averages may overlook clinically meaningful responses, highlighting the importance of individualized monitoring and rehabilitation approaches when managing pain-related asymmetries. Overall, this thesis demonstrated that the Nobel Ergometer provides reliable measurements of cycling biomechanics and lower limb asymmetry across repeated cycling trials. Using this device, we showed that movement evoked knee pain alters cycling biomechanics by reducing torque and power production in the painful limb and increasing reliance on the non-painful limb. A key finding was a large amount of variability in individual responses. While some participants demonstrated substantial unloading, others showed only small changes or even opposite changes. Together, these findings suggest that this ergometer is not only a reliable measurement tool, but also has the potential as a monitoring device for detecting pain-related changes in limb loading and rehabilitation. This may help clinicians identify compensation strategies and tailor interventions to the individual, rather than relying solely on group-based expectations. Future research should extend these findings by using this ergometer in clinical populations, particularly individuals with knee osteoarthritis, to determine if similar patterns of altered loading are observed. Further work should also include neurophysiological and perceptual measures to better understand the mechanisms that underlie individual variability and movement responses. I would just like to acknowledge everybody who played a part in this project, including Dr. Min and Dr. Jalal, who I spent many hours in both offices trying to unpack these results. And I'd also like to thank all the members of the iHad Lab group and APAD group, specifically Sharam, who had so much patience with me as I learned how to code, Amir for actually developing the electrical setup, Hamid, Reza, and Atusa all for helping with data collection and just for helping understand the results, as well as to all the participants who participated in my studies, because none of this would have been possible without any of you. And I really appreciate it. And I'd like to take questions now.
Floor is open for questions. Who would like to start us off? Right. Go for it.
Thanks for that. I really enjoyed that. I want to know a little bit more about the pain thing. And so how does it work again?
So basically what happens is the pedals read how much torque is being produced. It gets fed into the computer system, which then relays that back to the Arduino and the electrical setup, which then sends a signal to the electrical stimulator, which sends it to the participant.
Okay, and so the electrical stimulation, it's stimulating muscles around the knee, or it's going
The kneecap.
the
Yeah.
kneecap?
Okay.
Did you ever sort of look to see if you could quantify the individual's perceptions to the pain stimulus and how that related to the individual variation?
That was something I always wondered because I know how variable pain is. We were just going by, when we were finding their pain levels, it was a constant, how much is this? Is this, what level are you at? That kind of thing. But other than that, we didn't really have any other way of determining pain levels.
Okay. You can play off that.
Kind of playing off of that.
Yeah.
Since everyone's so variable,
Yeah.
did you actually try to relate their pain score back to the absolute voltage you gave each person? Because I'm assuming one person's 6 might be 50 volts,
Yes.
and another person's 6 is 150.
Exactly, yeah. So yes, we can do that. We tried to do that. One issue as well is depending on the pads or where they were placed, that also plays a role in how much pain they felt, right? So it's a really hard thing to quantify.
So I'm also wondering with the fact that it's like around patella, where you put them, that if you dial that voltage up high enough for someone that has a higher pain tolerance, you actually could be getting muscle recruitments, not just eliciting a noxious response.
Yeah.
So that could also play into some of your overcompensation. And so that might be for the people that compensated more to the pain leg.
Yeah.
It'd be interesting to look back at what was the actual voltage put in, because they might be compensating to it due to the fact that you've electrically stimulated the muscles are more active.
Yeah, that's actually interesting.
But this hasn't done on it, right? This has been done with I'll jump in. This has been done with sine wave versus a square wave. Can you explain that?
No.
So if you're inducing sine wave, there is going to be minimal muscle activation. But they have already done the Carroll study, they have already done square wave. Square wave can irradiate to the muscle, but sine wave doesn't. So
And
I've already seen the effect of EMG and it didn't do
Exactly, yeah.
And if I may, and how beautiful is that?
It was
Is
the
it just a
stimulation.
peak? Like, I would feel and then I went, or is it just pain all the time? Like, is it-
Yeah, so it's just during that push phase, right? So it's pretty much just you're going at 60 RPM, so it's basically once every second you're getting a jolt.
Oh, okay. Brent, do you want to continue?
I wanted some clarification around the conditions. So there was a high intensity power, low intensity power, high intensity torque, low intensity.
So there's basically two power outputs, low intensity and high intensity.
Okay,
And then one was at low intensity, there was one with pain, one without. And at higher intensities, there was one with, one without, and then that was repeated twice.
and the intensities were prescribed based on power or torque?
Yes, so low intensity was 20% of peak power output from the incremental test. The higher intensity depended on pain tolerance. Because what we would do is once we found the 2 out of 10 pain level at the 20%, we would slowly increase resistance until they reported 6 out of 10 pain, and then that was their higher intensity. I can tell you that it was around about 35 to 40% of peak power output.
Okay,
Mhm.
so then my question is actually, because I think probably a lot of people use power as kind of a guide when they're on bikes, whether they're in the gym or outside, they have power taps or whatever. And I think the pain is really associated with the loading, right? So it's the
Yeah.
torque, it's not the power. So
Exactly.
you can cheat a little bit by like increasing your cadence and decreasing your load.
Exactly.
Did you see and your pain in your study
Mhm.
it was driven by the amount of torque?
Yes.
Okay.
Yeah.
So did people cheat a little bit, or did they try to
So-
increase their cadence so the torque was lower?
Yes, under pain conditions, we were always watching the participants, okay, reduce your cadence, reduce your cadence, reduce your cadence. I can tell you for a fact that during the pain conditions, I was on them more than during the non-pain conditions. So yes, whether they were trying or not, they automatically try to go faster.
Okay, all right, interesting.
Mhm.
Thanks.
So actually a clarification, I'll complete right after, but a clarification on that, so you didn't increase the electrical stimulation intensity, only when they got to the 6 out of 10 was based on the increase in power?
Exactly, yes, they're pushing her on the pads. Mhm.
Yeah, slide 28, if you go back to slide 28. Okay, so.
I lost the external display. So,
I'm sorry, 32, not
32?
yeah, 32, okay. So here, I think that bell-shaped curve, the color of the positive should be white to match those
Yes.
bars, right?
Yeah.
So those who are in that region, in the positive region, it means that, somehow like they feel the pain, but they decided to apply more force in painful day,
Yeah,
right?
yeah.
What could be the reason? It's like against our hypothesis, right? That
Yeah.
We don't wanna,
Yeah, that one is. It could be people who are just trying to. There's too many possibilities, honestly. It could have been the stimulation wasn't up high enough. It could have been they didn't report true pain levels. It could have
can you see
been,
the bar graph, if just one more step forward. I think comes. Yes, here, okay, so how many days have like out of 23 participants,
about five for high intensity power.
in the positive region, how many have? I think 3 of them.
Yeah, both that.
3 out of 25, like 10% of participants. Yeah, I don't know what could be the reason. So were they like active, like, do you know some background about?
We looked at athletes, we looked at male versus female, we looked at all of that, and it just seemed
Specific.
random. Yeah, it seemed random.
Andrew and Joel?
But if they're pushing harder on that leg,
Mhm.
theoretically, they get through that pedal stroke quicker. You get through that phase quicker, and so if you're only ever being stimulated during that window,
Mhm.
you're probably, and you're telling us that you had to tell them to slow down.
Mhm.
I think the reason they're pushing hard on that leg is just because they know it's gonna end. Whereas if that stimulation was
Mhm.
chronic through the downstroke and upstroke,
Mhm.
you might get a different response. Because it's
Yeah.
like, it's like if you're walking across gravel barefoot,
Yeah.
you're probably gonna run, even though it's gonna hurt more, but you're gonna be through it sooner than if you walk really slow.
Can't you answer that question by analyzing the other phase of your data? Cause I know you only showed.
We-
results when
yeah.
You have it.
We did, yeah, we could, there's no, like, they weren't given any stimulation then, so how we differ, the only problem we thought about as well with giving them constant current is they're gonna get used to it, right? Potentially, so that might impact stuff as well.
And this is true.
Mhm.
We try to control the cadence though.
Yeah,
So did
Yeah.
you find any difference in the cadence?
there was no significant difference in cadence.
So there is a physiological probably explanation that, as an analogy, when you hit your finger with something, you're
Yeah.
squeezing, right?
Mhm.
This is what we call gate theory of pain.
Yeah.
Like you are increasing tension in the muscle or sensory area
Mhm.
around that.
Yeah.
To avoid pain. Could be this, like when you're pushing harder through the pedals,
Yeah.
it blocks pain to a certain level.
Yeah,
But I'm not sure if it's the case, but
Mhm.
gate theory of pain can explain parts of it.
yeah.
I have a question for you.
Yeah.
How indicative is this kind of electrical stimulation induced pain to like someone that has osteoarthritis or, a clinical population or an injured athlete that's rehabilitating?
Yeah.
With pain? Like, have you looked into that?
We would expect to be similar. It's like based on like all of the other experimental models that I've used, this model has been shown to be the most kind of similar to what they would feel. I honestly don't know what they would feel, but I would assume it's the closest and I assume we would get about the same results.
Yeah, because I'm curious if like you did a validation or like a follow-up
Mhm.
study with people that actually had pain and you weren't
Yeah.
on inducing pain, and you kind of compared them to healthy controls. Would you have as many people that increase the pain in that part?
Mhm.
Or could it be something like, this is pain that they're anticipating? They
Yeah,
know it's going to
exactly.
be unusual and it's
Mhm.
like an electrical stimulation,
Yeah.
so they're increasing
Mhm.
the tension in that.
Exactly.
Like, I'd be curious to see.
Yeah, it is, and it's such a hard thing because like, at least here we have somewhat of a verbal, okay, this is a 2 out of 10, 6 out of 10. With clinical populations, we have no idea how much they're feeling, you know what I mean? And I know a lot of people with like knee OA and they're just kind of used to the pain, so to them it's, you know what I mean? Yeah.
Yes, so did you try reproducibility with the pain study as well?
Like
Just to
between,
make sure that like the people
Mhm.
who felt
yeah,
pain in one leg or who
Yeah.
increased the load
Yeah.
on the pain leg, they did it again and again.
yes, yeah, so there was no significant differences between trials for high intensity, low intensity, nothing. Mhm.
And is it the same high intensity again tomorrow and it's the same
Yeah.
results? The
Mhm.
variability.
Mhm. It was all in the same
So
day,
it's the same.
Yeah, it was-
strategy.
yeah.
Sarah, I'm sorry, the question was about repeatability, so.
Yeah. Like
It-
between
it's
trial and
lost.
trial two, yeah.
Okay.
Mhm.
Yeah. You have this.
Yeah, I think they're like written, like, yeah.
Other questions for Sarah?
I have a question.
Go ahead.
What about the handle or sit post data under pain condition? So I wanna know if they make any change on their upper application.
Based on what I've looked at with handlebar, there was no change, no, but I haven't looked at seat books.
Actually, along those lines, there was one graph that you showed results for that. I think that was your first study
Yeah.
with the repeatability
Mhm.
and validity of it. So there was one graph where you showed that there was an effect of either time or workload on seat sway in the constant trial.
Mhm.
Can you just walk me through that result one more time? I think I like got confused whether there was a time effect or a
Yeah,
workload effect and what that really means in terms of interpretation.
yeah, let's see. You'll pull it up. Yeah. So, yeah, there's a workload effect for the seat post and yes, in the constant, with the constant load.
So that's what confused me, like, it's the constant load trial, so what does the workload effect mean in the constant load trial? To have an effect on the seat switch?
I believe that's how much they're differing between trials in seat post sway.
So I would expect that result would be other.
Yeah, but we wouldn't expect it, yeah.
Yeah, so
Mhm.
it was.
But there was no differences between trials, it was just a
Yeah.
significant effect.
Right.
Mhm.
Any other questions?
Oh, you just have it. I might have missed it. With the same experiment, did you try to alternate the phase between the legs and also see how the variability changes if you the same person? You do, I don't know, how long you test with, like 5 minutes on this leg and then 5 minutes on that leg.
So it was just randomized between if they got it on their right leg or left leg, but we didn't look at like if we put it on their right leg one day or left leg the other day, if it would impact it at all.
What's your hypothesis?
I suspect it would be about the same results, because even like we looked at, okay, if we put it on their dominant limb or their non-dominant limb, would that impact results at all? But there was nothing that stood out, so I think we'd probably see about the same results.
You have an online?
There's an online question, go ahead.
Hi, thanks. So I have a really boring basic science question. I love to see that you included that first study. You've got this new piece of equipment and you're saying, does it actually work? Is it actually a good measurement? And the way that you test that is by looking at the repeatability. And you say, this is awesome, it's really repeatable. So this is where I have a thought. Is repeatability on its own enough to tell us that this new piece of equipment or a new method is good? Can we kind of conflate these things here? Repeatability is good. But if my behavior is changing across conditions or across days, I don't actually want my method or my piece of equipment to be repeatable. So in the absence of a gold standard measurement here that you're comparing to, how do you know that that repeatability is good and not just a lack of sensitivity?
Good question. I mean, we can just go by the stats, I guess, and what we expect to see. And is there a bit of bias? Well, maybe, but we can't change the numbers. So the fact that the numbers are giving us what we're looking for and that it is repeatable, I would say that it is okay. Is that the best answer? Probably not.
Your sessions were the same day, though, right?
Different days.
Oh,
Yeah.
I thought you said you did the trial post.
For the first study, every trial was a different day.
Okay.
But for paint study, it was all the same day.
Just to add to your answer, we compared the force profile that we have from the pedals with what is in the literature. And then these pedal forces that we have, they've been already calibrated. So they're accurate up to, I think, plus minus 0.1 newton. But we also compare the force profile of what we got from the speaker literature. That's the very trust and sensitivity of the system.
All right, well, if there are no other questions for Sierra, hey, there's one more.
All right. It was really good.
In your first study, you looked at like the percentage of time over the
Yeah.
session. Did you do the same for each trial of your second study, looking at the first half?
It's funny, when I did pilot testing, I actually did. That's kind of what we started with. And are you wondering if there was differences kind of between the end and the, yeah, there was no differences between, now it's only a 2-minute trial as compared to some of these were like 10-15 minutes. But there was no differences just within the first 30 seconds and the last 30 seconds.
All right, let's thank Sierra for her talk.